Swayam Prabha. Digital India. Educated India.
Okay, this is called an odd cycle transversal problem, and so we'll come to it in one of the lectures, but I'll just state it. So this is given a graph G and an integer k, you output yes if there exists k vertices whose deletion makes G bipartite and no otherwise. Okay. Can you guess why is the name odd cycle coming here? Yes. Exactly. So basically this is a set of vertices whose relation kills all odd cycles in the graph, right? So basically what we had done in the previous example is we tried to look at vertex cover parameterized by odd cycle transversal. So yeah, I was on this point that we know that algorithm will work well for problems which have a small odd cycle transversal. Okay, so that naturally leads us to another kind of, like, one could parameterize the problem with its own solution, by which I mean, for example, if I have to find is there a small odd cycle in the graph, and if for that problem I can give you an algorithm, for example as of now, which runs in time 2 power k poly n. So if you are looking for a small odd cycle, your k would be small, right? So in this case this algorithm will be a polynomial time algorithm, right? So if I give you such an algorithm for odd cycle transversal, where, so basically here the parameter is nothing but the solution size. So if I give you an algorithm for odd cycle transversal that runs in this much time, and if you're looking for an odd cycle transversal of small size, this is indeed a very good algorithm. So in fact most of the problems that we'll see during the course of these 6 lectures, I mean their parameters will be of this form. Their parameters will be solution sizes, and these problems are interesting in itself. Of course structural parameters as in the kind of parameters that we discussed previously, they are also interesting, but for because the aim of the next lectures will be to demonstrate some techniques that people use to design such kind of algorithms, and for demonstrating them, these are like the problems where the parameter is the solution size. They are helpful in understanding the basics of those techniques well. So we'll mostly be dealing with these kind of problems where the parameter is nothing but the solution size. Okay. So basically for these problems I just wrote 2 power k for understanding. So we'll try to design algorithms of the form which have running time of the form some f of k, some function of k, I don't care, into polynomial in n. And note that this function of k, if you're talking about an NP-hard problem, it cannot be a polynomial function in k, because if it was a polynomial function in k, then we know k is anyway upper bounded by n, right? So you get a polynomial time algorithm for this problem. So this function better not be polynomial, it should be super polynomial at least. Okay. Fine. So okay, so this is the theme. So yeah, so in general just writing the abstract framework. So given as input an instance of a decision problem, like for example for vertex cover an instance of decision problem is a graph G and an integer k. For OCT it's a graph G and an integer k. So okay, first of all we'll be dealing with parameterized problems. So what are parameterized problems is what I'm writing here. So so input is a general instance of a decision problem, and along with that you're also given a parameter, some p. For example, we saw 2 possible parameters. Parameters could be, for example, for vertex cover we saw a parameter which is minimum size of a set of vertices whose deletion, okay, I'll just write OCT actually, now that you know what OCT is. So for vertex cover you saw a parameter which was the OCT of the graph. We could also parameterize it by k, and you can think of any parameter that you want to. You could parameterize it by the feedback vertex set of the graph. You all know what feedback vertex set is? Okay. So like think of the choices for parameters are numerous. So you can choose any parameter that you want to, and for any such parameter design an algorithm. Again, the answer that it gives are the standard yes no answers for the decision problem. So the parameter plays a role only in defining its running time. So the running time of those problems would be some f of p into polynomial in n. Okay. So this will be the general framework of the kind of problems that we'll be working with. So whenever I define a problem, it will be the input will be a standard instance of a decision problem, the output will be a standard output of the decision problem, but along with it I'll always define a parameter p, and we'll try to design an algorithm whose running time is like this. Okay, that's the aim. And one quick remark. So people, for NP-hard problems, people also try to design algorithms whose running times are of this form. Like again, fp is some parameter. For example, for vertex cover, let's say parameter being k, people try to design these. So people try to design these kind of algorithms also. And note that again. So for example, say as of now, let's just fix some f of k. Suppose f of k is some 2 per k. So now note that even if you have this kind of an algorithm for a fixed value of k, this is again a polynomial, right? So when k is equal to 1, this is n square algorithm. For k equal to 2, this is an n power 4 algorithm, right? So like if I say that okay, the kind of algorithms that I'm designing here, they are the running time will be polynomial for any fixed parameter value, then even for these kind of algorithms the running time will be polynomial for any fixed parameter value. Okay. But our aim will not be to design these algorithms. In a sense, these algorithms are better because note that their polynomial function is independent of the parameter, in the sense that for any value of the parameter, it is the same polynomial function. So for example, in particular, if I design an algorithm with running time some 2 power p into n square, then for p equal to 1 also it's an order n square algorithm, for p equal to 2 also it's an order n square algorithm, and so on. So the polynomial doesn't grow with the parameter, right? And in this paradigm it does. So again, it's your choice. Like for some problems these kind of algorithms are good enough, but that will not be our study motivation for our study. Okay, but on that note, can you give me a polynomial time algorithm for vertex cover for say a fixed k? When I say like k is a fixed number, choose any number, say 10, 20. Can you give me a polynomial time algorithm for vertex cover when say k is equal to 10? So I'm looking for a vertex cover of size 10 in the graph. And I mean, you can give me a polynomial time algorithm of this form also. This is assuming that the graph has 30 vertices, right? So the graph has n vertices. I'm looking for a vertex cover of size 10. Huh? Yes. How do you find that? Like, okay. The hint is don't think too much. Go to basics. I want you to give me I want to check if there is a graph, if there is a vertex cover in the graph of size 10, just 10. The hint is n power 10 is also a polynomial time algorithm, right? So what can you do?
Yeah, you can use dynamic programming.
Okay, let's go to even more basics. Yes, you can do that. Very simple. Like I can see you have learned a lot in the last 2 weeks. Right? Exactly. So pick, like look at all subset of 10 vertices in the graph. How many such subsets are there? So n choose 10, that is roughly n power t. And for that subset, just check if that forms a vertex cover. That you can do in polynomial time, right? You just have to check if for every edge there's an endpoint there. So basically, you actually have a polynomial time algorithm for vertex cover for every fixed value of k, right? And of course, that polynomial changes with as you change k. So if you are looking for a vertex cover of say 20, it will be n by 20 algorithm. Okay. So basically, for many problems, designing such algorithms is far more easier. We'll see an algorithm for vertex cover that runs in time 2 par k into maybe linear, that sort of an algorithm. So designing those kind of algorithms are far more tricky. In most of the circumstances, designing those kind of algorithms are far more trickier than these kind of algorithms. Okay. And okay, one more thing that I want to point out is, see, when I say I define parameterized problems. So when I say, okay, let us give an algorithm for parameterized vertex cover, note that this thing this thing as it is makes no sense. So when I say parameterized vertex cover, I have to tell you what parameter I'm talking about. As I said, there are numerous choices of parameter of vertex cover. For some parameters, you might be able to design an algorithm of this form for vertex covers. For some parameters, you might not be able to design algorithms of this form. Again, like NP hard problems, like classical problems, where you have a set of problems for which you cannot hope to get polynomial time algorithms. There are problems, parameterized problems, for which you cannot hope to get these kind of algorithms. Okay, so hopefully we'll cover that in the last class. In the course of these lectures, and there is a theory of hardness for these kind of problems also. So again, as people believe that P is not equal to NP, there are certain other sort of conjectures which people believe, and based on those conjectures, we can conclude that okay, unless that conjecture goes wrong, we can't solve certain problems in like this sort of a time, and we'll see those kind of things also. So there is a hardness theory for this setting also. Okay, so I have 15 minutes, right? So this was the introduction to what we are sort of going to do in the next few lectures. And again, each of the next lecture, we'll at least try to pick up a technique that people use to design such algorithms, and then using, with the help of that technique, look at some examples that use that technique to design such algorithms, okay? So I'll just start with one technique and we'll continue it in the third lecture. Like Sunil is taking the next lecture, so in the lecture after that we'll continue with that. But let me just define that. So you all have heard about pre-processing? No, okay, it's okay. So this is basically pre-processing, I'll come to it, and the technical term that's used in the literature of fixed parameter tractable algorithms is, okay, I didn't define that, I'll define that. It's called kernelization. Okay, by the way, again going back to this, if a parameterized problem admits this kind of a running time, we say that that parameterized problem is fixed parameter tractable. And the short term for this is FPT. So I think this term will most likely skip from my mouth often. I'll say FPT. When I say FPT, a problem is FPT, I mean it has an algorithm which has running time of this form. Again, when I say a problem is FPT, I'll say a problem with respect to a certain parameter. And in case I forget to define the parameter, you can definitely ask me what parameter I'm talking about. But in general, if I'm forgetting to define the parameter, I'll by default assume that the parameter is the solution size. For example, for vertex cover, it would be the k. Like if you're looking for a vertex cover of size k would be the parameter. For OCT, if you're looking for an OCT of size k would be the parameter in the default setting. If that is not the parameter, I'll define it explicitly. Okay, yeah, coming back to kernelization. So, okay, what is pre-processing actually? So, for example, when you have a large set of data, you try to pre-process it in a way that you want to throw away some irrelevant data, irrelevant information that you have. For example, okay, let us talk in this setting itself. For example, if you have a vertex cover problem, okay, I give you as input a graph G, okay, and that graph G has a lot of isolated vertices, okay. So I have given you a graph G. Of course, the graph G could be any complex graph, but in addition to it, it has a lot of isolated vertices. What can I say about these isolated vertices? I mean, the point is, we're trying to figure out, are these vertices of any relevance to the problem? At least intuitively everyone is clear, right? Like, if I'm looking for a vertex cover of size at most k in G, then I could as well, I could as well delete these isolated vertex from this graph and look for a vertex cover in the remaining graph. So these vertices are of, like, they're just redundant for us, right? So yeah, let's say this is the intuition behind preprocessing. Here it was very easy to determine these set of vertices that are irrelevant, right? So the idea of preprocessing is to identify some irrelevant structure in the problem and just throw it out, and with the aim of making the problem easier to understand or solve. Okay, that's the aim of preprocessing. So I don't know, but this preprocessing as a term, it has been there. It's not a new term that has been coined for the literature of FPT, of parameterized algorithms. It's not that. It has been there for a long time, but it like, people use it in heuristics, for example. People who design heuristic algorithms, they use preprocessing. But in general, for solving NP-hard problems, people people had always been unhopeful about preprocessing, because see, if in a preprocessing step I'm always able to throw a vertex out, and okay, one important point is, this preprocessing step is always a polynomial time procedure. So suppose you have an NP-hard problem and you do a preprocessing step. It's a polynomial time procedure, and you're able to throw away a vertex every time you do a preprocessing step. You have an NP-hard problem, and there is a preprocessing algorithm. What is it? It's a polynomial time algorithm that whenever you run that algorithm, it identifies an irrelevant vertex and throws it out. So suppose there was such an algorithm, what would you do? You have the input, you run this polynomial time procedure one time, you are able to throw away at least one vertex. For example, if it is a graph problem, you are able to throw away one vertex from the graph. You throw away that. Look at the remaining graph, again run this preprocessing procedure, and you are able to throw away one more vertex in polynomial time. So in n steps, you would be able to throw away all the vertices in the graph, right? And when we say throw away, as in you are always throwing away irrelevant vertices, or yeah, in some sense you are always throwing away irrelevant vertices. And so basically the point that I'm trying to make is, preprocessing for NP-hard problems where you try to throw away vertices at every step doesn't really make a lot of sense, because if you were able to do that at every step, you would end up solving an NP-hard problem in polynomial time, because you would throw away one vertex at the cost of a polynomial time procedure always. So that's why, at least when people used to do traditional in the traditional approaches, when people used to tackle with NP-hard problems, preprocessing was never thought useful. Of course, it was useful in the heuristic setting, but when you want some mathematical guarantees, it was never considered useful. But with the advent of fixed parameter tractability, preprocessing came into picture again, and we'll see what kind of things can we do with preprocessing. So again, I have some more time. So basically, what we try to do in FPT world is, we try to design a preprocessing algorithm, a polynomial time algorithm, with the following aim. We want to apply the polynomial time algorithm and throw away irrelevant parts until we are left with a small graph. Now, what is this small for us? Okay, so let's say we were solving vertex cover. So we were given as input a graph G and an integer k. So for this problem, for example, I would do preprocessing, by which I mean I'll run some polynomial time procedure, and I would want to reduce it to an equivalent problem. So like I would throw away some irrelevant vertices from the graph, and based on that I might want to change my budget k or not, so that is k prime, and I get this graph g prime here. The guarantee first of all is that both the instances are equivalent. By equivalent I mean if G had a vertex cover of size k, then G prime has a vertex cover of size k, by which I mean that we have only thrown away irrelevant information. Whatever information was relevant, we have kept it. And also the other direction. So if G does not have a vertex cover of size k, G prime should not have a vertex cover of size k prime. So we have not done anything stupid while doing this. So that's one thing. And additionally, so this is a normal pre-processing. You give gk and you get you do some polynomial time procedure and try to get an equivalent instance g prime k prime. But additionally, for example, for designing fixed parameter tractable algorithms, we demand that the size of g prime should be some function of the parameter. So for example, suppose we are dealing with vertex cover where the parameter is k. We would want that, we want to do some pre-processing, we want to do some polynomial time procedure, and at the end of it we want that the resulting graph should have size whose function is k. For example, let's say for vertex cover, here I don't even mind polynomial functions. So for example, suppose for vertex cover I am able to do some polynomial time procedure and get to a graph which is equivalent. So a yes here would mean a yes here, a no here would mean a no there, and its size is k square. First of all, do you think it should be doable, as in like it should be doable in the sense that if I do this, at least I don't end up solving an NP-hard problem in polynomial time. At least that should not happen. So suppose I like if I just give you this, if in polynomial time I have converted gk into an equivalent instance g prime k prime with the guarantee that g prime size is some k square, then does it mean that I'm going towards solving a NP-hard problem in polynomial time? But because if I am, then I definitely can't do this. Or in other words, I'm trying to ask you, if suppose I give you a graph g prime whose size is k square, then can you solve this problem in polynomial time? Do you see an algorithm in polynomial time trivially? I mean, if you don't, it's okay, because even I don't know of a polynomial time algorithm. Okay. So at least I don't know of a polynomial time algorithm, even if I tell you that this graph has size polynomial in k. Like it's not even like an exponential function of k. It's even if it's a polynomial function of k, I don't know if after achieving this step I can solve the problem in polynomial time. Okay. But suppose we are able to do this, then I can definitely design an FPT algorithm for this problem. FPT as in parameterized by k. So let me say some algorithm whose running time is, let me say, gk into polynomial in n. Can you see that? So if I give you a polynomial time procedure which takes as input gk and gives an equivalent instance g prime k prime, equivalent as in you wanted a yes no answer for this. So if I give you a yes no answer for this, it will be the correct yes no answer for that. So if it is a yes here, it is a yes here. If it's a no here, it's a no there. Okay. So if that's the property of g prime k prime, so definitely one thing is clear, that in order to solve the problem on this instance, it's enough to solve the problem on this instance, right? So now we have to solve the problem in this instance, and the guarantee here is that this instance has size k square. Then can you design such an algorithm for this problem? When I say this instance has size this much, let's say the number of vertices in this graph is k square. Then can you design an algorithm for this instance in this much time? Again, I'll repeat. So we wanted to see if there is a vertex cover in G of size at most k. Okay, I have given you the guarantee. How I have given you? I'll tell you later. I have given you the guarantee that okay, if you want to find a vertex cover in G of size at most k, it's enough to find a vertex cover in G prime of size at most k prime. Basically, I have told you that if this graph had a vertex cover of size k, that means the algorithm for this on this instance should return yes. Then the algorithm for this instance would return yes. That means this G prime would have a vertex cover of size k prime. Okay, And if it didn't have a vertex cover of size k, then this graph will also not have a vertex cover of size k prime. This is what I've told you. So what like you want, so if you want to say it's a yes for this, is there a vertex cover of size at most k, you can just check if this has a vertex cover of size k prime. If it says yes, you just go and say yes for this instance, right, because this is the guarantee that I've given you. And if this says no, it doesn't have a vertex cover of size at most k prime, then you just go and say no for this. This is okay, right, because this is the guarantee that I've given you. This is how these instances are related. I mean, we'll see how to get to this, but this is the guarantee I've given you. Now modulo this guarantee. Now, so basically what is the problem now? We have to solve on G prime, we want to find out is there a vertex cover of size k prime. Now this is what we have reduced our original problem to. Okay, this is clear. So we want to find is there a vertex cover of size k prime in G prime. This is the problem now. Now additionally I have told you that the number of vertices in G prime is only k square. Okay, so as here I should also say, let's say I also have this, that G prime is this, and let's say k prime is at most k. K prime is at most k. We just saw an n choose k algorithm for vertex cover, right? For 10 vertices we saw n choose 10 algorithm. So what would an n choose k algorithm give for this instance? N here is k square, k here is k prime, which is at most k. So an n choose k algorithm here would be k square choose k algorithm, right? So this is k power 2k algorithm. This is some f of k, some g of k, right? So you have those many possibilities, and each of the possibilities you want to check if basically you are choosing a k size set from these k square vertices, and you want to check if this k size set is a vertex cover of this graph or not, which can be done in polynomial time, right? So basically, how much time have you taken to solve this problem? You would have spent some polynomial time here plus some k square choose k time. So basically the time that you have spent is actually some polynomial in k plus k square choose k time. So this at least as of now looks like polynomial into some g of k function, and I leave this as an exercise as of now. It's not difficult to see that such an algorithm can be thought of as an algorithm of this running time also. Like of course this running time may be like, let me say this is some g prime. So you can write this running time, like if you want to write this as this expression, a multiplicative expression, you can write this like this for an appropriate g. Okay, so that's not hard. Or in other words, if you don't want to try that, you can think of when I defined parameterized problems, I said we are looking for running times of this form. You can also say that we could have also defined it like this, that we are looking for running times of this form or of this form. Both these notions are equivalent. So if you have a running time of this form, you can write that down as a running time of this form, and if you have a running time of this form, you can write it down as this form. So this you can take as an exercise. It's a simple exercise.